Magnus effect. The Magnus effect is a concept of fluid dynamics, derived from Bernoulli equation, that is a result of spinning spheres or cylinders moving forward through a fluid. When the Magnus effect takes place, the object will be deflected from the path it would have taken if it wasn't spinning. We have conducted an experiment to demonstrate the Magnus effect. In our experiment, we connected the end of two cups together with tape to simulate a cylinder. We will call this the object. Coil a long piece of elastic band around the object before launching it off. Roll the clip.
10.
As you can see, the cup deflected upwards. If the object had no rotation, it would probably continue in a parabolic motion. However, what we observed in our experiment was that the object deflected upwards still even as it was approaching its natural path's maximum point. What you just saw in the clip was a Magnus effect at work. When the object was released from the elastic band and launched off, it started to rotate in an anti-clockwise manner. If there was no spin on the object, the separation point of the airflow on the object would be at points 1 and 2, and their flow would be distributed as shown. The velocity gradient at the surface of the object at points 1 and 2 would be 0. However, due to the angular velocity induced on the object, this separation point has been shifted to 3 and 4, since the object has its own speed now. Therefore, the flow distribution at point 1 and 2 will look like this and shows that points 1 and 2 will no longer be our separation points. Instead, the points where the velocity gradient is 0 will be at points 3 and 4, as shown. Because of this shift in separation points, the pressure distribution around the object will also be shifted due to its angular velocity. Without rotation, the pressure distribution of the object should look like this. Because of the incoming airflow on the front of the object, there is a positive pressure area at the front of the object and a negative pressure around the rest of the object. Due to the rotation of the object, since the separation point shifts anticlockwise, the pressure distribution will also shift anticlockwise, as shown. This results in a higher area of negative pressure above the object than under it. Since the force acting on the object due to this negative pressure can be represented from area multiplied by pressure, the upward force acting on the object is greater than the downward force, creating a lift. Hence, the resultant force on the object is upwards, explaining why the object deflected upwards.
Here is another experiment we did to demonstrate how the shape of the object contributes to the Magnus effect. For this experiment, we rolled two different objects, a ping pong ball and a cylindrical roll of paper, down an elevated slope before falling to the ground. As the object rolls down the slope, a spin is generated. This results in an angular velocity present while the object is mid-air. First, the ping pong ball is rolled down the slope. We then marked where the ball landed on the floor. We then repeated the experiment with a roll of paper, which has a higher projected area than the ball. As you can see, the roll of paper didn't travel as far as the ping pong ball. Assuming that both objects left the slope at a similar velocity and considering the shape of both objects, due to the higher projected area of the paper roll will experience greater lift. Lift, which is perpendicular to the direction of the free stream, causes the object to deflect away from its original path. This explains why the paper roll deflected further backwards as compared to the ball before landing, thus demonstrating how the shape of the object contributes to the Magnus effect.
The Magnus effect shows up everywhere, and if we are able to recognize it, we may be able to take advantage of it. Whether we are looking to improve our football kick, table tennis game, or even just looking for a fun hobby project, understanding the Magnus effect will give us some idea on how to do it better. And even if you are not looking to make or improve anything, being able to recognize the Magnus effect in everyday life will give you an appreciation for the engineering and design that usually goes unnoticed.